Hello viewers, welcome to this lecture on optimal control for discrete systems. In this lecture, before going to the optimal control problems, we will find the procedure for optimizing the functional j of k0 given by this expression summation k ranges from k0 to k0 plus capital N minus 1 of the function capital F of xk plus 1 comma k. So, this function capital F is a function from Rn cross R into R here. So, this is to be cancelled. So, it is a real valued function of vectors from Rn, and xk is a sequence of vectors where k ranges from k0, k0 plus 1 etc. So, we have to find a sequence of vectors xk which minimizes the expression j of k0. In some problem it may maximize. So, in this lecture we will find this necessary condition for finding the optimum value of this expression. So, the necessary condition may provide the either maximum or minimum value, or it may not provide any of this also, because it is only a necessary condition. So, for finding the optimum value of j, the necessary condition is the variation in j should be equal to 0. Del j of this expression is equal to 0. So, to calculate this del j, we will obtain the necessary condition as follows. Given in this theorem, the Euler-Lagrange equation for the minimization of the expression 1 is given by this expression. The partial derivative of f of xk plus 1 k with respect to xk plus the partial derivative of the function f of xk minus 1 xk k with respect to del xk, that should be equal to 0 is the necessary condition. The boundary conditions are given by this expression. The partial derivative of f of xk minus 1 f of x of k minus 1 by del xk, this has to be equal to 0. Now, we can observe that the boundary condition, for example, if the initial and final conditions are fixed, initial instant is k0, final instant is k0 plus n. So, if the two conditions are already given in the problem, then the variation will be 0 at these 2 points. So, this condition is not required. In case that these are variables, the initial position x of k0 and final position x of k0 plus n are variables, then the variation will be arbitrary. In that case, we will get a boundary condition given by this del f by del x at these 2 points should be equal to 0. So, that we will see during the example. So, let us see how to derive this necessary condition. So, if x star k is a optimal sequence in between the instant k0 to k0 plus n, then the variation is given by this expression. So, we note that first we derive this theorem for the case where x of k are not vectors, they are scalar functions. So, the same expression can be derived later for the vector functions. So, that can be easily generalized. So, right now we are assuming that f is a function of this real valued functions xk plus 1 and k is a real number. And so, now x of k, x star k is a optimal sequence. So, the variation in x star k is given by del x k. So, it gives a new sequence x of k, and x k plus 1 is the sequence starting from x star k plus 1 plus del x of k plus 1. So, see, if you assume that for the real case k 0 plus 1 etc. k 0 plus n. So, the optimal value at k 0, x of k 0 is a number, x of k 0 plus 1, x of k 0 plus 2. So, if we have some sequence like this, this is our optimal solution. Now, if you give a variation in the first value, it may be a small variation here, positive variation, and there may be a negative variation like this. So, we may get a new function which may be given by this expression. So, it is like x of k. If this we are assuming to be x star of k for various values, a small increment will give a new function x of k, this sequence. And similarly, if you start from the next value, for example, if you start from k plus 1, that is another sequence which is given by x of k plus 1. Now, the j value which we want to minimize is given by this expression starting from k 0 to k 0 plus n minus 1 of this function, and after giving the increment in x star we get the function j delta. So, the first variation in j is delta j is j delta minus capital J, and which can be written like this by directly substituting the values from here. J delta is this, j is this, subtract this 2, we get this expression. Now, if you write the Taylor series expansion of, so the first variation in j is given by j delta minus j, and if you observe from the previous slide, j delta is the expression 6. Now, it is having f of x star plus del x and x star k plus 1 plus del x of k plus 1 comma k. Now, expanding this expression in the Taylor series and taking only the first variation in the Taylor series. So, we will see that the first term of the Taylor series is same as j, and j delta minus j, in that the first term will get cancelled. The second term is the first variation given from the equation 6, which is nothing but del f by del x of k into del x of k. Similarly, the derivative, partial derivative del f by del x of k plus 1 multiplied by the first variation x of k plus 1. So, that is what we will get here, the del f by del x star k and del f by del x k plus 1 term. Only first variation we are collecting and omitting all the second variation, we get del j to be like this, and this should be equal to 0 is the necessary condition. But from here we may not get any useful result. So, we can further proceed like this. We take the second term, the second term is the del f by del x k plus 1, and we write the entire the summation k equal to k 0 plus k 0 to k 0 plus n minus 1 for the second term. So, if we expand it term by term, we get this expression. For k equal to k 0 is the first term, k 0 plus 1 is the second term, etc. The last term is for k 0 plus n, and then we add this term and subtract this term, that for convenience del f of x star k 0 minus 1 x star of k 0 minus 1 term we add and then subtract the same thing. Now we can combine this term except the starting from the first term to this term we can write it in the particular form. So k 0 to k 0 plus n minus 1 del f of x star of k minus 1 x star of k minus 1 by del x star of k etc. And while writing like this we are omitting this term that is the last term, because we are writing it in the form of k minus 1 appearing first. Here we observe that the first values are f of x star of k 0, but when we write it in the form of k 0 minus 1 as the first term. So we have to note that while doing that way we will be omitting the last term in that previous series, and this term we have already introduced artificially the last step. So these two terms are omitted and this summation takes care of all the other terms. See, this last term is not there inside the summation and this last term is also not there in the summation. So we take this term as well as this minus term and combining these two here separately we get the entire expression which we want here. Okay. So the second term was written in that particular form. The first term is as it is. So combining the first term of the equation 8 and second term of 8 together we will write the equation to be like this. These are the expression we get del f of x star k minus 1 x star k minus 1 by del x star of k into the variation x of k, and the last two terms extra terms which we have taken is written in this particular form. So combine this is only the second term of the necessary condition. The first term is here as it is. So combining the first term and the second term together we get this, and the boundary condition term is given in this way. So now the variation del xk is arbitrary, this entire bracket has to be equal to 0 here, and for the boundary condition we have to, because once the bracket becomes 0 the remaining gives the boundary condition for the solution of the problem. So we get the necessary condition to be like this: del f of xk plus 1 k by del x star of k plus del f x k minus 1 x k and k minus 1 by del x k again equal to 0 is the necessary condition, and the boundary condition is given by this expression, this bracket. So now depending on the case, if the boundary conditions both of them are fixed values, then the variation at these two boundary will be 0. Here the variation del xk, I think it should be del xk also. So this correction also we have to remember. Okay. Equation 13. So this del xk, if the initial time k at k0 and k0 plus n, if x of k0 is given, x of k0 plus n, if both are given then the variation at these 2 points will be 0. So this condition is not required, only the equation 12 to be solved under these boundary conditions. But in case x of k0 is given but the final position is not given, final time is given k0 plus n, but x of k0 plus n is not given and it is free, then we need the boundary condition from here. because the variation del x of k 0 plus n will be arbitrary in that case. So, we get a condition del f by del x star evaluated at k 0 plus n should be equal to 0 will turn out to be the boundary condition for such problem. So, for the case 1 we have to solve only the equation 12 with the given boundary condition, and in the case 2 where x of k 0 is given and the other one is free, then we get this boundary condition. So far what we have seen is the derivation of the equation, this two equation 12 and 13, where x of k is a real number, the sequence x of k is a real sequence, but in case x of k is a vector sequence, each x of k belongs to Rn. So, if x of k belongs to Rn for each k value, then also the procedure is same, only thing is x of k is written as x1 of k, x2 of k, etc. xn of k, it is a vector. So, at every stage we have to replace the real value with the vector, and then the partial derivative of this function with respect to each value should be considered. So, for I is equal to 1, 2, 3 up to n, we get this two formulas. Instead of 12 and 13 formula, we get 16 and 17 for each variable I, each variable xi, okay, the same formula. So, the procedure will be the same exactly. So, now we will consider a simple problem of finding the optimum value, optimum sequence. So, find the optimal sequence for minimizing the functional j k 0. K 0 indicates that is the initial instant. So, if it is given by this expression x square k 0 plus 3 plus summation So, it is summation k equal to k 0 plus 2 of. So, let us consider the function j, yeah, yes. So, in this problem we consider the functional j of k 0 is given by summation k starting from k 0 to k 0 plus 2. And the expression is x of k and x of k plus 1 plus x square of k plus 1. So, we have to minimize this expression, and so it means under the condition x of k 0 is 1 and x of k 0 plus 3 is some value, these two values are given. So, we have to find k 0 plus 1, k 0 plus 2, k 0 plus 3. So, 4 instant of time is given, x of k 0 is fixed, it is 1. and k0 plus 3 is also given, it is the value 4. Now we have to find the values for this k0 plus 1, k0 plus 2, two values we have to find. So the optimum solution, it may lie anywhere in this line. The values can be anywhere here, only initial and final are given. So if we solve the equation del, the solution, we have to solve the two equation which we have mentioned in the previous slide. So that is del f by del x, when f is starting with x of k, and del f by del xk if f is starting with k minus 1. So here f, we can write, if it is starting with k, it is the given expression x of k plus 1 plus x square of k plus 1, and when it, the initial thing is starting with k minus 1, it is x of k minus 1 x of k plus x square of k. So the necessary condition is del f k by del x of k plus del f of k minus 1 by del of k equal to 0. So that is the condition, okay, that as given here, and we do not require the boundary condition 17 because both boundaries are fixed here. So we simply write del f by del k, derivative with respect to k, it is x of k plus 1, and del f of k minus 1 by del x k, if you differentiate this with respect to k. So this is the first one, the second one is with respect to x k, we get x of k minus 1 plus 2 times x of k. So this is equal to 0. Now we put k equal to k0 plus 1 in this equation, we will get x of k0 plus 1 plus 1, k0 plus 2 plus x of k0 and plus 2 times x of k0 plus 1, that is equal to 0. And when we put k equal to k0 plus 2 in this equation, we get x of k0 plus 3 plus x of k0 plus 1 plus 2 times x of k0 plus 2 equal to 0. So we get this two equation, and it is already given x of k0 is 1. So we have to solve this two equation. From equation 1 we will get the relation between x of k0 plus 2 and k0 plus 1 equal to 0, and k0 plus 3, x of k0 plus 3 is given as 4. So we substitute it in the equation 2. So that gives you 4 plus x of k0 plus 1 2 times x of k0 plus 2 equal to 0. So we get two equation with two unknowns. The two unknowns are x of k0 plus 1 and x of k0 plus 2 in this equation. So we get the solution, solving these two algebraic equation, we get the optimal value of this thing, of the four values are given. So we will get some value for x of k0 plus 1 and some value for x of k0 plus 2. already x of k0 plus 3 is given. So, this sequence is the optimal sequence which will optimize the expression j of k0 under this condition. Okay. Now, if the final condition is not given, let us assume that the initial condition x of k0 is given, but final condition is free. So, that we can solve by this expression. So, now as second example we will see the example in which the boundary condition is variable. So, here we consider k varies from k0 to k0 plus 2 of x of k plus 1 plus x square k plus 1. So, we have to minimize this expression under the condition x of k0 is some given value and x of k0 plus 3 is free. So, which is not given. So, in that case we have to solve So, for this problem we have to find the optimal sequence. We have to find x of k0 is already given, we have to find k0 plus 1, x of k0 plus 2, x of k0 plus 3. These 3 values we have to find to minimize or maximize this expression. So, we have the solution is we have to solve the equation del f if it is starting with xk and differentiate with respect to this, and del f if we start with k minus 1 and we differentiate this equal to 0 under the boundary condition x of k0 is already 1, it is given, and because the second boundary condition is free from the expression here, we will see that the del f starting with k minus 1 derivative with respect to x of k at the end point that should be equal to 0. So, we have the boundary condition del f starting with k minus 1 term of del of xk evaluated at k0 plus 3, that should be equal to 0. So, this is the problem. So, if you write the equation will be the same because the problem expression is the same as in the previous slide here. So, these two equation will be the same, only thing is the boundary condition we have to substitute this expression. So, del f x of, if you write k minus 1, that term is nothing but x of k minus 1 and x of k plus x square of k. We differentiate with respect to del x of k. So, that gives x of k minus 1 plus 2 times x of k. So, if you evaluate at k0 plus 3, so this evaluated at k0 plus 3 should be equal to 0. So, this implies x of k0 plus 3 minus 1. So, it is k0 plus 2 and plus 2 times x of k0 plus 3 here, that is equal to 0. So, we get a relation between k0 plus 2 and k0 plus 3, and already we have the two equation number 1 and 2 here. So, we substitute the relation, this relation between x of k0 plus 2 and k0 plus 3, we can write one in terms of the other. So, that will reduce one of the variables, and we can solve the system using the initial condition by substituting x of k0 equal to 1 in this two system of equation 1 and 2, and making use of this boundary condition at k0 plus 3, we can solve the algebraic equation easily and obtain the optimal sequence for the 3 values, that is x of k0 is already given. We want to find x of k0 plus 1, k0 plus 2, k0 plus 3. So, this sequence is obtained by solving the simple algebraic system. So, in this lecture we have seen the optimization of a discrete expression, discrete time expression, and the optimum sequence, how to find the optimum sequence to minimize j has been shown, that is the necessary condition has been shown here. And in the next lecture we will consider the optimal control problems, that is along with the minimization of j, the constraint is a discrete control system, and we will find the optimal control for the discrete time systems. Thank you.